Okay, so we have the problem is like that if XD is a metric space and given f a function from x to x which is 1 1. Okay, XD is a matrix and given f x which is 1 1. Then we have seen in a previous video whose links is down in the description. If we have another metric d dash on x defined as, how d dash is defined? D dash defined d dash xy is equal to d fx comma fy. Now the questions start from here. Are d dash and d are equivalent matrices? Are equivalent metric? Okay, this is the question. Okay, if you don't know the definition of equivalent metric and what are equivalent metric on a set and what are its properties, I will make a video on this and put it on the description. Okay, if you know well, then just go ahead. Okay, now we will start. Is it true or false? Okay, that's a question. So I will finish the suspense here, and this is not true. Okay, it's a false statement, and I will give a contradicting example. But first we will see that an equivalent metric, okay, it preserves completeness. Okay, it preserves completeness. That is, if like we are comparing, if we are given d1 and d2 two metric on same space x. Okay, so if x comma d1 is complete and d1 d2 d1 comma d2 are equivalent, then we have x d2 is also complete. Okay, we're gonna use this result. If you want proof of this, I will make a proof of this also and put it on the description. We'll give it a link in the description. So question, okay, so this is how we're gonna find a contradictory example. We will show that there exists a metric space X with D here is complete space. Okay, and we will see that there is a function f from x to x which is 1 1, and then the metric d dash xy which is defined as d fx comma fy. We will show this that this x d dash is not a complete space. It's not a complete space, and hence D and D dash are not equivalent. Alright. Okay, for the counter example, we are taking x is equal to r, and D metric is the usual metric on R. I think everyone is aware about this. It's just simple modulus function. And for f, we are taking fx is equal to tan inverse x. We are taking fx is equal to tan inverse x, and this is a 1-1 function. No doubt, I think about this. We know its graph looks so great. Kind of this is pi by 2 is minus pi by 2. Okay, this is a 1-1 function. So this function will induce a metric called d dash, which is defined as d comma fx comma fy. Alright, so we know that R with the usual metric D is a complete space. Okay, but we will show that R with the D dash is not a complete space. It's not a complete space. Okay, for that we need a sequence. How will you show something is not complete? We will find a sequence xn, which is Cauchy in R T dash, but does not converge. Right, this is how we're gonna prove. What is the sequence? We take the sequence xn to be. We'll see how it is constructed when you see the proof. We take the sequence to be 10 pi by 2 minus 1 by n. Okay, we have taken this sequence. Right, no issue here. Okay. So what we need to show? We need to show that this xn is a Cauchy sequence. It's Cauchy in RD dash. Okay. So for that we consider d dash xn comma xm. What does look like according to the definition? It will be fxn comma fxm. Okay, which is equal to d. What is f tan inverse tan pi by 2 minus 1 by n, comma tan inverse tan pi by 2 minus 1 by m, and inverse and tan will be cancelled, and we get d pi by 2 minus 1 by n, comma pi by 2 minus 1 by n. And d, what is this? This is d, the usual metric, the norm, the mod in R, and this will be equal to 1 by n minus 1 by m. Simple calculation. This can be make less than epsilon for some n naught for all nm greater than equal to n naught. We have done this from very basic knowledge of real answers, nothing new. Okay, so hence we have shown that, okay, you can see we have shown that xn is a Cauchy sequence in Rd dash, not in usual metric. In Rd dash is a Cauchy sequence. Now we will show that this xn does not converge in Rd dash. Remember, in Rd dash. Okay, let's assume it does converge. Okay, say xn, we will prove this by contradiction. Say xn converges to some a in Rd dash metric. Remember, I keep emphasizing on this in Rd dash. What does this mean according to this? What does this mean that d xn comma a converges to 0? Sorry, d dash xn comma a converges to 0. Now we put the definition of d dash xn comma a. What is that? It's actually d f xn comma fa converges to 0. Now what is that? We know d is the usual metric and fxn is nothing but pi by 2 minus 1 by n. We have seen this from here above. See here. Okay, and this is the mod, so we get pi by 2 minus 1 by n minus fa converges to 0. Okay, we have now, let's see, I will write the last step again. It's like pi by 2 minus 1 by n minus fa mod converges to 0. What does this show? This shows that fa is equal to pi by 2. I don't think it's anyhow difficult to see. It's a very easy thing to see. You can see that fa is equal to pi by 2. Alright, but note that what was our f? Our f was fx was 10 inverse x. Yeah, do you agree? So what we have shown that 10, there exists an a such that 10 inverse a is equal to pi by 2. But what is the range of range of 10 inverse x? It's minus pi by 2 to pi by 2. It does not attain pi by 2. So what happened here? So what really happened here is that we have a contradiction that xn converges to some a. This is not possible. So xn is a Cauchy sequence which does not converge. In Rd dash. Thus Rd dash is not a complete space. And we are done with our proof. Complete space. Okay, so we have shown that d and d dash are not equivalent metric. You can okay, now proof is another quadratic example is done, but we can observe that somehow this things happen because the function we have chosen, its range is not a closed set. No, you can see the pattern. What is happening? It's not a closed set. It's an open. Yeah? And we have constructed a sequence for which we have shown is not pi by 2 minus 1 by n. Look where it converges. It is converging to pi by 2. So somehow the range of function is does play a role here. So my question is that can we generalize this result? I don't know really, to be honest. I don't know myself, but I think I can generalize this if I can see a pattern that if the function range is not closed, then we can definitely construct some sequence like that. I think I'm gonna make a video on this and I'll put in a description if anyone interested. Yep. Okay, done. Bye.